Alright, ladies and gentlemen, this is the IA number 2 practice exam for physics. There are a lot of questions here. There are 32 questions for you guys to practice through the concepts that you guys need to know for this upcoming IA, mostly on forces and circular motion. Let's start with number 1, where we're given a data table of 4 different objects with 4 different masses and speeds. So we're looking for the object with the greatest inertia. So what we're looking for is just the mass. Mass only affects inertia, nothing else. So we're looking for the one with the greatest mass, and that's right here, object D. Alright, number 2. Which situation describes an object that has no unbalanced force? No unbalanced force. That's a mouthful. So let's think about, let's just say, unbalanced force. That means we are not in equilibrium. Oops, I can't English right now. So unbalanced meaning not in equilibrium. Whereas no unbalanced means the opposite, we are in equilibrium. So that would be not choice A, not choice B, it's choice C, because we're looking for something that's at rest or constant motion. And that is a hockey puck moving at a constant velocity across the ice. Alright, number 3, which body is in equilibrium? So following the same idea, we're looking for something that's constant velocity or at rest. So that's choice D, sliding at constant velocity across the tabletop. Number 4, we have 2 forces acting on a box, F1 and F2. If you look at the sizes of those arrows, they're not the same. And question says if magnitude of F1 is greater than F2, F1 is bigger than F2, that means we're going to be pulled more towards this side, to the right, because of F1 being bigger. So when you have this unbalanced force, that means we have acceleration. It's not balanced, it's not the same. Unbalanced, which means F net is not 0 newtons, and so we got an acceleration. So accelerating in the direction of F1 because that's the bigger force. Number 5, which quantity is a vector? So magnitude and direction. We did not talk about power, we did not talk about kinetic energy, but we did talk about speed and weight. Speed only has magnitude, it's a scalar. Whereas weight is a force and forces are vectors. Choice D. Now number 6. We have 3 forces acting on a box in an inclined plane as shown in the diagram below. If the box is at rest, that means everything here is balanced out. So if everything is balanced out, the net force is always equal to 0. That means friction and normal force and weight are balanced out by something. Okay? So that means friction is balanced out by the parallel component of the weight, Fg parallel, and that the normal force here is balanced out by Fg perpendicular, the perpendicular component, okay? Number 7. Which 2 graphs represent the motion of an object on which the net force is 0? So that means we're in equilibrium. And when that happens, that means we're either at rest or constant motion, constant velocity. So we're looking for graphs that show constant velocity or rest. None of these show at rest, so we're looking for something that has constant velocity. Now looking at each of these choices, we could cross out C and D, looking at the distance graphs. Because if you notice, these distance graphs show exponential changes, it's not constant. So these 2 show constant velocity for sure. Alright, now we have to look at which one of these speed versus time graphs shows constant speed, constant velocity. Choice A shows an increase in velocity, increase in speed over time, you're accelerating. But choice B shows it stays the same constant value, so it's choice B. We're looking for something that shows constant speed or at rest. Alright, number 8, a new 25 Newton horizontal force northward. So 25 here versus 35 down here with a 15 kilogram box. So we're looking for the acceleration. So F net equals ma. Our net force is the difference between these two opposing forces. Opposing forces meaning that you have one side stronger than the other. That means we take the difference. Our net force here is 10 newtons. Our mass is 15 kilograms. And we're looking for A. So 10 divided by 15, A is equal to 0.67 meters per second squared. Choice A. Now number 9, still the same idea, F net equals ma. So when you have two forces opposing each other, it's going to be at its weakest point. Versus if you have something in different angles and stuff, it's going to be kind of slightly stronger, but if you have two forces on the same side, it's a lot stronger. But here we're dealing with two forces in opposite directions, so it's a weaker force. So we take the difference. 10 newtons again is our net force. Our mass is what we're looking for. And they gave us the acceleration of 2 meters per second squared. Squared indicates its acceleration, not no square. 2 meters per second is not acceleration, guys. Meters per second square is. So the mass is 5 kilograms. Number 10, a carpenter hits a nail with a hammer. So, nail with a hammer. The magnitude of the force that the hammer exerts on the nail. So hammer to nail. I can't English right now. And then we're talking about what about the nail to the hammer. So we're dealing with the same pair of objects. So these two pair of objects are interacting with each other. It's the same force being exerted on each other. The same. Newton's third law. Number 11. A 400 Newton girl standing on the dock exerts a force of 100 newtons on a 10,000 Newton sailboat as she pushes it away from the dock. How much force does the sailboat exert on the girl? So girl exerts 100 on the boat. How much does the boat exert back on the girl? Also 100. So you need to read these carefully. Okay. Number 12. A 60 kilogram physics student would weigh 1560 newtons on the surface of planet X. What is the magnitude of the acceleration due to gravity on the surface of planet X? So we're looking for G using this equation. Fg, the weight, equals mass times G, acceleration due to gravity. We're looking for G. Okay? So they gave us the weight something that's about closer to 10. So it's a little more than 10. So let me erase that. So you get something that's a little closer to 10. And then 180, that means they're on opposing sides. There's 10 here, and this one's 2. That means you're going to get a resultant force that's 8 newtons, okay? So when they're acting together on the same side, so as long as they're on the same side, they're going to have the greatest magnitude in terms of the resultant force. So imagine 2 people pulling together on the same side, tug of war. They're definitely going to have much better results than if they're pulling at opposite ends or at different angles, okay? As long as they're pulling on the same side, pushing on the same side, greater resultant force. All right, number 21. Which vector represents the force that would produce equilibrium? That means something to balance out these two forces. So this is our net force between both of these vectors. The one that would produce equilibrium, the equilibrant, is the one that goes completely opposite but equal in magnitude, so that's choice C. Number 22 is an 8 Newton block accelerating down a frictionless ramp inclined of 15 degrees to the horizontal, as shown in the diagram below. What is the magnitude of the net force causing the block's acceleration? So it's accelerating downward, and it's because of what force? Now, if you notice, there's no friction because it's frictionless. So that means the only force pulling it downward is Fg parallel. Now, if you think about the phrase, sine goes down the incline, the parallel component goes down the incline. So Fg sine theta is the equation we're going to use. The weight they already gave to us is 8 newtons. So Fg parallel is equal to 8 newtons, the weight, times sine of 15. Okay, so 8 degrees times sine 15. So 8 times 0.26 after you're doing sine 15. And then Fg parallel, which is the net force, times 8, so 0.26, you get 2.07 newtons. Okay, and that is closest to choice B, 2.1 newtons. Number 24. What is the component of the truck's weight parallel to the hill? Fg parallel, Fg sine theta. Okay, so they already gave you the weight in newtons, 1.0 times 10 to the 5th newtons times sine of 8 degrees. So you just plug and chug into the calculator. Oh my lord, guys. Times, that's 100,000. That's a big number. Fg parallel is about this much, 14,000 newtons. That's a lot. Choice C. There we go. Okay, number 25. Block weighing 10 newtons is on a ramp, inclined at 30. Oh, hey, I gave this question out in class. That's fun. What is the magnitude of F? So this is constant velocity. That means F here is balanced out by the force of friction and Fg parallel. Keep in mind, it's not listed there, but it's always there. It might not be written, but it's always there. So we already know force of friction is 3 newtons. For Fg sine theta now is 10 newtons times sine of 30. 3 plus 5, which equals 8 newtons. Choice B. Number 26. What is the approximate magnitude of force F? So that means this force F is being counteracted by Fg parallel because we don't have friction. We don't have to worry about that extra thing there. Okay, but they gave us the mass. That means we need to convert that mass into newtons. Fg equals m times g. 10 kilograms times 9.81 meters per second squared. Oopsies. Equals 98.1 newtons for the weight. We're looking for Fg parallel, which is equal to F. Okay, because it's where R it rests. equilibrium. So Fg sine of 30, 98.1 newtons times sine of 30, which is 1/2. If you guys remember from trig, then you don't have to plug that into the calculator. And you get about 49.05 newtons, which is 49.1 newtons. Choice B. Voila. All right, number 27. Which vector best represents the direction of the normal force acting on the box? All right, so let's label each of these forces here. Vector B shows our normal Fg. That's always pointing downward. Vector A is the Fg parallel, the one that goes down the incline. The one that goes into the incline is Fg perpendicular. And then vector D opposes the motion because the things like to go down the incline. So that's force of friction. So that leaves vector C. Now keep in mind, the normal force comes out of the surface. It's directly coming out of the surface now that our surface is inclined. So normal force is vector C coming out of the surface like that. Number 28. Okay, we got a car traveling at a constant speed around a circular curve. Ooh, circular motion, guys. Circle, circle, circle. That's our mass. That's our speed. That's our radius. Looking for centripetal acceleration. So AC equals V squared over R, no mass needed. So 12 meters per second, and we square that over 30 meters. 144 over 30, and that's equal to 4.8 meters per second squared. Number 29, a 1750 kilogram car travels at a constant speed, that's mass. So this is speed, around a horizontal circular track with a radius of 45 meters. What is centripetal force? All right. So centripetal force on the reference table is listed like this. If you look at our previous problem, AC is equal to V squared over R. You can combine both of these together to get FC is equal to MV squared over R. And we can plug and chug and to get our answer. Plug and chug, I don't know where that came from. You know what? I remember, it was from high school. We called it plug and chug. So if you do this math, you get 8,750 newtons, choice C. Let's change up the color. You know, I like green. It's very underrated. Okay, we have a diagram with 4 points, a car on the bottom of the circle with a bunch of numbers, but we're looking for the centripetal acceleration of the car at the position shown. Okay, centripetal meaning towards the center, because it's Latin. So that means if we're going to look at this car and point towards the center, it's going up towards C. That's always the case for centripetal acceleration and centripetal force. Number 31. An athlete in a hammer throw event swings a 7 kilogram hammer in a horizontal circle at a constant speed of 12 meters per second. The radius of the hammer's path is 2 meters. You know, I never tried some field events. I used to run track and stuff, but I'm very interested in learning some field events besides long jump. I want to try hammer throw. I feel like that would be fun. Did you know I'm going to try to help out with outdoor track this year, guys? Look out for me in the spring. Anyway, here we have the hammer being released at the position shown. Which point will it travel? Okay, so we're moving in a clockwise fashion. Woo! Swinging, 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 then it's going to release. Okay, so when you release at a certain point, the object's going to move in a tangent straight line fashion. So it leaves the circle in a straight line fashion, not following the curve of the circle. It's not going to curve that way. It's going to leave and move tangent to the circle. So at this point, it's going to move this way, upward, this way, towards point B. If the circle were traveling in a different direction, going counterclockwise, it would go towards point D. So that's the velocity vector. Number 32. Draw the direction of both the object's velocity and the centripetal force acting on the object when it is in the position shown. So this is an example when it's going counterclockwise. So velocity, again, is tangent going straight out of the circle, and then both the force and the acceleration are both towards the center like that. Okay, and we finally reached the end of this video. There are 32 problems, but you guys made it to the end. Good job. Give yourselves a pat on the back. All right, clap it out, clap it out, clap it out, guys. Anyway, I highly suggest you go still review some of the old topics like circular motion and forces. Definitely a lot of forces. Review that forces test, guys. Don't make the same mistakes you did in the first test, okay? All right, now adios. Bye-bye.